please join me in welcoming Dr. Madhavan Nair to the stage.
Good morning to all of you. First of all, thank you, Mr. Anand, for inviting me to participate in this global summit and also to give a keynote address on climate change. So I thought I will give a small presentation. So because seeing the things will help you to understand what I am talking. But it will be very brief. I'll take about 15 minutes to tell the story what I want to say. And so I'll start. There's little science in it. So I'll very briefly discuss about science. So our whole Earth system. So we have so-called equilibrium. So because we get we survive because we get solar energy. That's a driving force, driving energy. Solar energy gets heated. So because of solar energy, we get heated up our Earth system. At the same time, the Earth system also emit radiation out to the space. So there is an equilibrium of what we get and what it goes out. So if any imbalance between this equilibrium can really cause climate change. So why that should happen is mainly because of so-called the increase in gases like carbon dioxide, for example. The carbon dioxide we call as a greenhouse gas because it allows the solar radiation to come inside the Earth to the surface, but doesn't allow the so-called Earth's radiation to go out to the space. So what finally it does is it traps more radiation into the system, so it gets heated up. It's almost like our body. We get a lot of energy, but then if you don't lose the energy, our temperature goes up, right? The same way our Earth system also. If the Earth is getting more and more energy, the temperature will go up. So the increase in carbon dioxide in the atmosphere is measured at a place called Mauna Loa in the US, and this is the David Keeling is the person who really started developing instruments and taking observation. It's a place called Mauna Loa in the US. And it very clearly shows the concentration of greenhouse gases is going up, carbon dioxide is going up. That is mainly because of industrial activities, deforestation, and more of into energy consumptions, etc., and land use changes, etc. And this is very evident. Only thing is the present US government has closed down these observations. So you cannot really assess these observations now because the present US government doesn't believe in climate change. Okay, so because of, as I said, the greenhouse gas is increasing, so our temperature will go up. So this global warming is happening. The top one shows how much temperature has increased for the last 123 years or so from 1901. The bottom one shows how much temperature has changed for the last 30 years. And the scale is same. So you can really see that warming is happening everywhere. And it's not uniformly, but warming is happening everywhere. And last 30 years, the warming is much more appreciable than warming we experienced for the last 123 years. And land is warming much more faster than oceans. And Arctic region is warming much more than any other region, so we call Arctic amplification. And the Earth has warmed almost 1.2 degree from pre-industrial period. That's a substantial number. And last year, 2024, was the warmest year ever recorded using observations. And what is the effect of climate change? It can really give more frequent weather extremes, increase in sea level, because sea is nothing but water, so thermal expansion can happen. And melting of sea ice, especially on Arctic Ocean, glaciers, melting of glaciers, retreating of glaciers, tropical cyclone can be more intense, and another important aspect is ocean acidification. And the question is, your global warming is happening. I was mentioning about extremes can increase. So do you have an evidence that extremes are increasing, weather extremes? The answer is yes. So this picture very clearly shows, especially you see the green, that's all flood, and also the pink colors, that's all extreme weather. You can see that with this is from 1970 to almost 2023. You can see the substantial increase in the frequency of extreme weather events like flood, and also the extreme weather like thunderstorms, heavy rains, etc. And you can see how the earthquake and volcanic activity, which is nothing to be related to human activity, they are almost same. Every year it's almost same. So what is changing is basically extreme hydrometeorological events. So it is very, very clear evidence. And this is a very interesting plot I wanted to show because some of you are all basically the entrepreneurs, etc. So this is the report called the Global Risk Report 2025, 20th edition, It's prepared by World Economic Forum, which you all will know. Who are those people? It's very, very important organization. So what they have done is they identify the risk, climate, not only the climate risk, it's a risk for the whole global community for the next 2 years as well as the next 10 years. And they have plotted the graph. The x-axis is short-term severity for 2 years and long-term severity for 20 years. And if the number is more, the severity is more. What you can see at the top, extreme weather events, biodiversity loss and ecosystem collapse, critical change to Earth system. These are all the most critical risk which we are going to face. We are going to face next 2 years as well as we are going to face in next 10 years. World Economic Forum is not mentioning about anything about economy. They are all mentioning about the extreme weather events and what is related to the Earth system, climate change. So what we have to really appreciate that the whole community, global community has accepted this climate change is going to be a very, very important aspect which we need to think about it. We need to not only think, but we need to really worry about it. And of course, there are some technology, there are some outcomes like adverse outcomes of AI technologies can be, for example, next 10 years, it can be really a great risk, global risk. So that's why I mentioned here is a point of no return. By 2035, there could be a lot of things which they say it's a points of no return. The question is, do you have points of no return already in the climate system? The answer is yes. This is a very famous paper which I published a few years back, which says Arctic sea ice, Greenland ice sheet, Amazon rainforest, for example, coral reefs in Australia, near Australia, Atlantic circulation, West Antarctic ice sheet. These are all have reached a situation in which the further damage can really lead to point of no return. For example, Amazon rainforest can completely disappear, Arctic sea ice can completely melt out. By 2050, people expect that in winter, in their summer, September for example, Arctic Ocean will have no ice, which is a very, very important aspect. 2050, they are expecting that Arctic Ocean will not have any ice by September. So these are some of the things which they expect. So they are all points of no return. The question is, how will you know what will be the future climate change? So we developed the model called Earth system model. It's a highly complex mathematical models, which includes a lot of physics. So we treat the 5 spheres, and we also, the right hand side, we see all the physical process which occurs in the Earth system are being covered. Solar energy, what is the radiation going out, clouds, a lot of chemistry involved, precipitation, hydrosphere, all these interactions, very, very complex system. Everything should be modeled in a mathematical model. That we do, we call Earth system model, the model which describes all the components of the Earth system. And so we need observations for doing everything. So do we have observation? The answer is yes. Left hand side shows that the comprehensive observation system we call Global Climate Observational System, which includes satellites, international aircraft, ships, drifting buoys, the ocean, and there are observatories on the land, we call surface observatories, automatic weather station, radio zone, all these things. And right hand shows that satellite provides a lot of information. A right hand figure shows how many satellites we have now in the system, in the space, to help the climate observation. You can see a big bunch of satellites. Okay, so now question is, then this model, the system model has a mathematical equations. It's all nonlinear partial differential equation. We have to solve it using some particular mathematical methods. We either follow finite difference or spectral methods. Then we have, these are the grid points in which we do the calculation. We divide the whole globe into different grids. And how much grid size is important. If you really have better better computers, you can have a higher resolution. So we, in our Ministry of Earth in India, we started with a model with 37 kilometer by 2010, and that is now last month, we have now model of 6.5 kilometer. That means every 6.5 kilometer you can get one observation, one forecast, one scenario. And so this blue is basically the computer which we use to do these calculations in terms of petaflop. Petaflop is 10 power 15. That means 5 petaflop means 5 followed by 15 zeros. Flop means floating point operation, right? 1 second. This is 1 second. This 1 second, 5 into 15 zeros operation. Operation means 2 plus 2 is an operation. So 2 plus 2 is 4. So this operation 5 followed by 15 zeros operations will be done in 1 second. That is the speed of the computer which we use. So now the latest computer is 22.3 petaflop. This is the fastest computer available in this country. Of course, it costs about 1,000 crore. And this is the two computer. This is the computer when I was secretary, we purchased about 450 crore. With this called Pratyush. Now the Arca is the latest computer. Both are in the institute in Pune, where I was also the director of the institute. This is the way how the computer has developed, how reformed, especially the computer which are used for climate change studies. 1990s, we used to have teraflop machines, which progressively, steadily, the speed has increased. And mostly you can see US is playing an important role. And China has recently have two big computing system. And Japan earlier had a computer called Air Simulator. So now the US is expecting there will be a computer with the exaflop mission, 10 power 18 speed. So that is the computing system which they are expecting to develop for climate change simulations. And now I will just brief you why the models, you need models with a high resolution, mainly because the top one is our latest model with 6.5, bottom one is our earlier model, right hand side shows observations of rainfall. You can see that in the top one, you can see that even in the day 5 forecast, the observed rainfall pattern was picked up by that model, but in the bottom it is not really good. So you need higher and higher resolution models to pick up the extreme weather events. That is the message which goes. So how far you can go to higher resolution is the question. And this is very interesting. So I will put a question to you. There are 4 maps, out of which one is observation. Remaining 3 are models produced by weather prediction models. Can you differentiate which is observation, which is model? Very difficult, isn't it? I'll tell you. The bottom right-hand side is observations. The remaining all models. The left-hand side is the model with 1.4 kilometer resolution. The grid point is 1.4. The global model. You can see how much computations are required. And you can see how good the resemblance between observations and the model 1.4. Even in minute fractions of the clouds over the Atlantic Ocean, etc., is picked up by the model very well. So this paper has very categorically told that if you really want to represent very minute fractions of the clouds, you need to have a very high resolution model. Now the whole global community is now asking for 1 kilometer model to be developed. The problem is you can easily do it, but then question is how much computing power is required. This is a very interesting part which shows that model resolution, if you increase it, how much computing cores you require and how much power consumption you require. You can say it's not linear, it's highly exponential. So if you go from 5 kilometer to 1 kilometer, you can see the sharp increase in the computing resources you need and also the computing power you need, huge power. If you from the present model to 1 kilometer, present model is for 50 kilometer for example, to 1 kilometer, you will need 10 power 20 times increase in the computing power, 10 power 20. That is the kind of computing resources and knowledge. So you need huge computing power. And so if you really want to see the future of climate change, this is a beautiful report. When I was secretary, we prepared it. It's a downloadable, it's freely available on website. You can see how much it is there. And so where we are heading for in climate modeling is we are going into exascale computing now. The next leap in exascale computing is becoming a reality now. So, but you need huge involvement in terms of computer experts and electronic engineers, etc. And AI/ML learning integration is we are trying to do it because that can really help us to decrease the energy efficiency, energy use, and especially to improve the model simulations. So that is the one area where a lot of people are working on now, AI and ML learning integration. And we need, so for example, if you use a bigger computer, you need more and more energy, isn't it? So we are talking about climate change, you are developing models, but then that should not, the models themselves should not use more energy. That's meaningless. Okay. And so energy efficient computing is a very important area where we are working on. And of course, it can be driven by renewable energy like solar and wind, and also more personalized impact-oriented projections we really want to make, and global democratization of climate computing like our cloud computing which we do. We want to develop models which anybody can use it just to give from their particular places. And what are the challenges with the data center? So if you really want to develop a bigger computer for example, 1 kilometer model, you need a huge computer, you need huge resources, huge facilities, infrastructure. Then so the basic problems is high energy consumption. So accounts is now present data centers of climate centers, it accounts about 2% of global electricity use. Okay, so this leads to significant carbon footprint. And the second is it produces huge heat. It's a lot of heat it produces, so extensive cooling systems are required. Now the innovative cooling systems are based on water, just water sprinklers. And some cooling system use evaporative cooling which consumes large quantity of fresh water. So where water is not really available, so you cannot really put this up, the data centers. So what are the solutions we have? We can transit to 100% renewable energy sources like solar, wind and hydro. Energy efficient computing, we should really think about it. Better chip design in processors. So there are two big players who makes these processors. One is Intel, another is AMD. And use of AI for optimizing power use, locating data centers in cold climates. Google has done it. Many people are doing it. Amazon has done it. They put the data centers into Arctic region where the temperature is very cool. And some people even put under the sea so that the temperatures are very cool. So you don't need so much energy to cool the system. And implementing circular economy for some practices of hardware recycling. The quantum computing is another major area where it can really help us. The quantum computing is an emerging area now every day, everywhere. Even in India, we have now launched a quantum mission in which quantum computing is a component. And so how can quantum computing can help? It can really improve the numerical modeling, the oscillator numerical. I told that we had to solve the partial differential equations using some methods so that the quantum computing can really solve. So we do a processing called parallel processing. So we need, our codes are parallel processing based codes. So we need to do the oscillator numerical modeling using quantum computing. Data assimilation, we assimilate a lot of data into the model, and we can also do a lot of climate change prediction and uncertainty. And machine learning for whether you can do is using quantum machine learning and more of energy efficiency. So basically it provides more speed, scale and efficiency needed to tackle its most complex environment system using quantum computing. But it's not going to happen next 1 year or 2 years. My gut feeling, I'm not an expert, but my gut feeling is another 8-10 years it may take for India to develop a quantum computing for weather and climate. So there are, I have already 2-3 slides more. So strategies to combat. So climate change is happening. We all know extreme weathers are happening. So what we can do? So there are two big things which our whole global community is talking. One is adaptation. You adapt to what the situation is happening. If the temperature is increasing, you adapt to increasing extreme weather events, you adapt it. So adaptation is one part. The second is mitigation. Mitigation, nothing but tackling the root cause. You remove the emission of greenhouse gases like carbon dioxide, methane, etc. So transition to renewable energy, solar, wind, hydro is an important aspect. The Indian government, all of you know that Indian government is fastly, they are going into renewable energy sector now. They are investing a lot of money. The ratio of electricity produced by renewable energy is increasing substantially. But still, coal is still being used as important energy sources. So energy efficiency in buildings, transport, industries, climate smart agriculture. It's called, sometimes you must have heard about precision agriculture, where you don't put water everywhere in the field, but specifically at some places. So it's called climate smart agriculture, sustainable land use. Adaptation, you can have building resilient infrastructure, developing drought resistant crops, improved water management and early warning systems you can develop, and urban planning to reduce heat stress. These are all some of the things. For all these things, you need technology. So these are all to be done. So we are talking about climate change because all the countries we say that climate change is happening, but then all people we need to develop. So we need development. So we cannot stop emission of greenhouse gases, carbon dioxide. We cannot stop industrialization. So then people talk about sustainable development. You can develop your country, but then you do it in a sustainable manner. So these are all sustainable solutions. So you need technology for this kind of sustainable solutions. So developing technology for sustainable solution is an important area where we need to concentrate. There are plenty of opportunities where startups can be developed for solving these issues. And this is one good example how the agriculture sector how technology can be used in adaptation of agriculture. You can you can use remote sensing data, big data, artificial intelligence, Internet of Things, IoTs, nanotechnology, robots, blockchain. All this technology can be used to adapt agriculture sector to climate change. So this is a very important area where many people are working on, but the number of startups in climate tech, so-called, in India is very, very small. So but my suggestion is opportunity is very big. So we need to really jump into and start doing this kind of technology development. Then another concept, this is probably one of the, last but one slide, is all the countries have agreed that we will go for net zero emission. That means whatever we are emitting should be the same as what is being absorbed by the system, air system. Carbon dioxide is a very mixed, uniformly mixed gas. Once you emit it, it will be there in the atmosphere for the next 30, 40, 50 years. You cannot simply take it out. So it will lie there. So even if you stop all the emission, you close down all the factories, you stop everything, industry, everything now, but still the carbon dioxide emitted few years back will be still floating in the atmosphere. So what we need to really do is reduce the emission. That is very important. Cut down the emission, which many countries are not very committed, but we need to do. So that the red curve, you can see that with the time you can start reducing the the carbon dioxide emission, greenhouse gas emission. But the green is basically the process in which we absorb the carbon dioxide from the atmosphere. So if you really do both, so there will be sometime that you can expect a kind of net zero emission. What is emitted is also absorbed. India has committed that we will do it by 2070. Almost some 45 years later, we will do this net zero emission. And many countries are really committed for 2050. So there are many options which we can do it. For example, human-made carbon removal, we can do it. Natural-based carbon removal, we can expect. So this is the philosophy of net zero emission. So then many people talk about how the absorption, the net negative emissions can be achieved. So a new concept called is geoengineering options. This is really it is very nascent stage. Just people are talking about R&D. There's not much investments has been made, but it's a broad, very wide thinking. But so there are two important. One is solar radiation management. Aerosols means small particles. You can take it to 20 kilometers and you can put it so it will reflect the solar radiation. Marine cloud brightening, space-based reflectors. You can put mirrors out to the space so that solar radiation is reflected back. And carbon dioxide removal is afforestation we can do, and reforestation. Direct air capture from the atmosphere can be done. There are a lot of technologies being developed now. Ocean fertilization. As I told that ocean is a very important component of the system where the carbon dioxide emitted, 25% of carbon dioxide emitted from the atmosphere is absorbed by ocean. So ocean is a natural absorbing process. But so if you really increase the fertilization, the ocean can really absorb a little more. The enhanced weathering and soil carbon sequestration. These are some of the options we have. It's all technology. So last step. So let us make our commitments to save our beautiful blue planet simply because we don't have a planet B. I'll stop here. Thank you.